So we're going to have a look at one factor ANOVA. So one factor ANOVA is where we're having a look at the effect of a single factor, and it's where we're having a look at the variance between more than two groups. So to measure the different factors level, we must measure observations differently to follow a hypothesis that we are tested. So our H0 is that all the mu's are going to be the same for I equals 1 to k, and H1 is going to be mu I is not equal to mu for I is 1 to k, where at least two of the means differ. So mu I is the population mean for level I, so each group that we have has different levels. Now I have still included some old information about how this used to be calculated. However, we're not going to use this method here anymore. So our assumptions when we're doing a one factor ANOVA. So when applying a one factor analysis of variance, there are three key assumptions: that our observations are independent and random, that the population at each factor level is approximately normally distributed, and that the normal population has a common variance. So we are going to be creating a one factor analysis of variance table that will look something like this. And you are given some of this notation in your formula booklet, some of these definitions, which are on page 7 in the formula booklet. I am going to go through, it's a bit confusing when you're just looking at it like this, so I am going to go through one example where the question is done completely by hand, and then I'm going to do one example where I'm showing you how to do this via the graphical calculator. So here we have the table below shows the time, so the lifetime under controlled conditions in hours, in excess of 1,000 hours of samples of 60 watt electric light bulbs of 3 different brands, and we're trying to assume all the lifetimes normally distributed with a common variance. We're testing at a 1% significance level that the hypothesis that there is no difference between the brands with respect to the mean lifetime. So our H0 would be that mu I equals mu for I equals 1, 2, 3, and our H1 would be where mu I is not equal to mu for some I equals 1, 2, 3, where at least two means differ. Now for the method done by hand, the first thing I'm going to do is I'm going to just pause the video so that I can copy this down here and do some working below it. Okay, so I've just made myself a little copy of this table just so that I can do some working around it. And the first thing I'm going to do is I'm going to find the totals for these rows. So I'm going to have T1, T2, T3. So in my graphical calculator, just in the normal calculator bit, I'm going to have 16 plus 15 plus 13 plus 21 plus 15, and that gives me 80. Then I'm going to have 18 plus 22 plus 20 plus 16 plus 24, which will give me 100. And then I'm going to have 26 plus 31 plus 24 plus 30 plus 24, and that gives me 135. The other thing that I need to find is my total. So my total is going to be what I get when I add these three numbers together. So 80 plus 100 plus 135, which gives me 315. I also need to know my NI. So my NI is going to be 3 because we've got 3 groups here. Sorry, it's going to be 5 because I've got 5 in each group. And then my overall N, well, I've got 3 lots of 5, which means my overall N is going to be 15. The last thing I need to be able to find is my xi's squared, my xij's squared, which literally means I'm squaring each of these numbers and adding it together. So I'm going to have 16 squared plus 15 squared plus 13 squared plus 21 squared plus 15 squared plus 18 squared plus 22 squared plus 20 squared plus 16 squared plus 24 squared plus 26 squared plus 31 squared plus 24 squared plus 30 squared plus 24 squared. And we're going to put that into our calculator. You could also go to the stats part of your calculator. You could type all those numbers in. So 16, 15, 13, 21, 15, 18, 22, 20, 16, 24, 26, 31, 24, 30 and 24. And then if we go to calc, check that our set says list 1, 1 because we haven't got any frequencies. And then if we go to 1 var, we can see the sum of x squared is 7,045. Okay, so we can check that in that bit or we can calculate it there. But I would write down what I'm doing if you were doing this without the graphical calculator. So then we're going to find our SST to start off with, which is going to be the sum of the xij's, which is this here. So 7,045 even, minus t squared, which is 315 squared, over n, which is 15. So putting in the normal part of our calculator, that gives us 7,045 minus 315 squared over 15, which is 430. Then we need to find our SSB, which is going to be the total for each group squared over the number of pieces of data in that group. Minus our t squared, our total squared, over n. So putting that into our calculator, gives us 310. And then we can start to make our table that we just saw on the previous page. So across the top, we are going to have our sum of the squares, followed by our degrees of freedom, followed by our mean of the sum of the squares, followed by our F ratio, which is going to be our test statistic. Down the side, we're going to have between, in this case, the brands. Then we're going to have within the brands. And then we are going to have our total. So the first thing is our SST was 430, so we put that there. Our SSB, so between the brands, was 310, which means that this value here is going to be the difference between these two, which gives me 120. Now the degrees of freedom for between the brands is going to be, for within the brands is going to be the number of groups that we have here minus 1. So that's going to give us 2 for between the brands. Then our total degrees of freedom is the number of pieces of data that we have up here, which is 15 minus 1, which gives us 14, which means the missing piece of data that we have here is 12. Then to get the mean of the sum of the squares, we're going to do the sum of the squares divided by the degrees of freedom. So for between the brands, we're going to have 310 divided by 2, which gives us 155. For within the brands, we're going to have 120 divided by 12, which gives us 10. And for the total, we're going to have 430. Sorry, we don't have to do it for the total. We only do it for these two here. And then for the F ratio, we're going to do the between the brands divided by mean of the sum of the squares, divided by the within the brands mean of the sum of the squares. So we're going to have 155 divided by 10, which gives us 15.5 for our test statistic. So our F value, which is our test statistic, is 15.5. To find the critical value, in our formula booklet, we're going to go to pages 21 and 22. For this question here, it was a 1% significance level. So that means that we're looking at the table which is 0.99. And we're going to go across by the degrees of freedom between the brands, down by the degrees of freedom within the brands. So we're going to go 2 across and 12 down, which gives us 6.927. Be careful here because it's not a symmetrical table, so you will end up with a different critical value if you look it up incorrectly and go across by 12 and down by 2. So then as the test statistic is bigger than the critical value, we reject H0 at a 1% significance level. There is sufficient evidence to suggest there is a difference between the mean lifetime of the 3 brands of light bulbs where at least 2 differ. So that is how we would answer the question without using the function in our graphical calculator. So now I'm going to show you how to do it using the functions in the graphical calculator. So we have the exact same question again, but now we're going to look at how we do it using the graphical calculator to help us. So our H0 again is going to be that mu I equals mu for all I equals 1, 2, 3. our H1 is going to be that mu I is not equal to mu for some I equals 1, 2, 3, where at least 2 means differ. Then in the calculator, we're going to enter our data into the stat mode. And the first thing I'm going to do is I'm going to say where my piece of data is. So for the first brand 1, we've got 5 pieces of data. So I'm going to have 1, 1, 1, 1, 1. Then I've got 5 bulbs of brand 2. So I've got 2, 2, 2, 2, 2. Then I've got 5 light bulbs of brand 3. So 3, 3, 3, 3, 3. Then in list 2, I'm actually going to put my data. So I've got 16, 15, 13, 21, 15. Then I've got 18, 22, 20, 16, 24. Then we've got 26, 31, 24, 30, and lastly 24. So list 1 is saying where the piece of data is. List 2 is saying what the actual piece of data is. So then we're going to go into test and then ANOVA. Where it says how many, we want that to say 1. If it doesn't say 1 already, you can click F1 here and it'll change it so it says 1. Factor A, which is what kind of brand of bulb it is, we put that into list 1. We put whether it was brand 1, brand 2 or brand 3 into list 1. And the dependent, the actual lifetime of the bulb, we put that into list 2. So that's our dependent. So that needs to say list 2. And when I click exit, it will come up with my table. Now there's 2 things to note which are common and good practice, is that here our SS column and our DF column have switched positions, so I would switch those back. And also we're missing our row for our totals, which I would also add in. So we're going to have between the brands. Then we're going to have within the brands. And then we're going to have total, which I'm going to add on there. Across the top, like I said, I would swap those columns back so that I had my SS, my DF, my MSS, and my F. So I'd have 310, 120, which add together to give me 430. I have 2 and 12, which add together to give me 14. I have 155 and 10. And when I divide those, I get 15.5, which is my test statistic. My critical value, remember, I'm going to go across by 2 and down by 12, looking at 0.99, which gives me 6.927. So then as the test statistic is bigger than the critical value, we reject H0 at a 1% significance level. There is sufficient evidence to suggest the mean lifetime of the 3 brands of bulbs is not the same, where at least 2 differ. So you can see how much quicker and easier it is to use this function in the graphical calculator. However, if you have 2 blocking factors, so that you're doing a Latin square design, you would not be able to do this method, as you can only do 1-factor ANOVAs and 2-factor ANOVAs in the graphical calculator. I'd now like you to try the Now You Try, and thank you very much for listening.